Good morning, everyone. This is a second webinar organized by the Direction Project about emergency response for battery fire. So we will cover different aspects related to battery fires, and the objective of this seminar is to share knowledge, share information with you about the type of fire we can expect with battery, in particular lithium-ion battery, and also look at the solution, especially for emergency responders, how to fight this kind of fire. My name is Olivier Salvi. I will be the moderator for this webinar, and I am the coordinator of the Direction project. We will have today as well Perola Malquist from Utkiken company, Amandine Lecoq, a researcher as Ineris and also in charge of testing of batteries, and Lena Ulveman from the company Colcut System, developing some solution, especially for firefighters. During the webinar today, we will have a first part which will be with the different presentation, mainly related to the emergency responder perspective. First, with Perola, who will explain what are the difficulties faced by emergency responder, firefighter, when they have to deal with a fire in a car, a fire of battery. Then we will have Amandine presenting the research insight, what is the level of knowledge for the different type of batteries. They are not all the same. We have different hazards, and it's important to know about it. And the third presentation will be by Lena about the technology developed by Colcut System, the Cobra technology, which has been tested and gives some very interesting results. We will learn about it. And after this series of presentation, we will have a Q&A session where you can enter in the Q&A part of the webinar your question, and we will address your question after the presentation. We plan to finish at around 12:15, and hopefully it will be for you an interesting webinar. Some preliminary remarks related to the Direction project, which is organizing this meeting, this webinar. So this is a project funded by the European Commission under the European Union's Horizon Europe program. This is a network, which means that our objective is to develop some activities that are useful to share knowledge, to share information, data in the field of disaster resilient society. So the objective in particular of the project is to promote innovation, facilitate the innovation uptake, and help for the development of innovative solutions for emergency responders. So we have several moments or several activities in the project. The first activity is to understand the needs of responders so that we can identify the capability gaps that are expressed by the responder. We do some screening to identify some potential solution, and also not only solutions that are technology, but sometimes also knowledge, so standards, good practice, and this kind of information. And we promote and help facilitate the sharing of this knowledge among the community of emergency responder and stakeholder in the network. And when there is no solution available, we stimulate the co-creation, the co-development of innovative solutions by bringing together researchers, technology developer, and emergency responders so that they are working together. So we have different activities in the project, which is to support the interaction with different network, different association. In the project Direction, we are working with the CTIF, which is the International Association of Fire and Rescue Services, with the European Federation of Firefighter Officers, FEU, with the Austrian Red Cross, with the Firefighter Academy in Portugal, ENB. So all of these organizations are more or less network, and we try to coordinate the sharing of knowledge among this network. We are also supporting the research programming at European level, of course in interaction with the European Commission, but also with national research agency and other foundation. As I mentioned earlier, we support the technology development, the co-creation, and we try also to promote nice, interesting solutions that have been developed to a wider audience, to a larger market, as we did recently with the awards, the Direction Awards that you can find on the webpage of the project. And we are doing that in particular to ease the procurement process, which sometimes is it's quite complex and quite long. So we try to speed up and to facilitate the procurement process for innovative solution. And of course, as all networks, we are looking at how to maintain the network after the support from the European Commission. So we are working on the sustainability. This webinar is also organized in the framework of the Disaster Resilience Society Stakeholder Hub, which is an initiative that consolidates the results from different projects in the field of disaster risk management. So you can access this platform with this QR code and this web address. So the idea of this DRS Hub is not only to deal with different projects, but to behave as a cluster and to facilitate the interaction between different projects to develop synergies and to enable cross-learning and cross-innovation between the different projects. So I think it's enough what I wanted to tell you. Now I would like to invite Perola to take the control and to start his presentation.
Thank you very much, Olivier, and thanks for having me here. I am Perola Malmqvist, a fire protection engineer and former battalion chief from Sweden. Right now I'm working with Utkiken, which is my company that is a knowledge hub for the Scandinavian countries, mostly Sweden, but some more countries. And in this presentation, I'm speaking on behalf of CTIF, which is the International Association of Fire Services. And that's an organization where I'm a member, and I try to share my knowledge there, and I also gain a lot of knowledge from the CTIF. And talking about battery fires, so I've been involved with the Swedish Civil Contingencies Agency to first try to see if it was possible to put out battery fires. And when we saw that it was possible, we've been working on first a demonstration report about how to do it, then an emergency guidance for how to do it in a safe way. And we've also presented on the Fire in Vehicles conference on Iceland this year. So the first test we did was in 2021, and we presented the tests at 2023, and then the guidance at 2025. And basically, what we did was to show that if we get water into the battery pack by penetrating it, we can extinguish a battery fire, and it can also be done in a safe manner. And here is the key to what we are talking about. If you look at this, you see thermal runaways for a couple of seconds, and then it's a regular fire. And during this process, we heat the adjacent cells. And by getting water into the battery pack, what we do is we cool the cells that are on fire with thermal runaway or fire afterwards, and we cool the adjacent cells. So that is basically the key, to get water inside and then cool as much as we can. This is a video, a clip from Netherlands Fire Brigade, which illustrates it very well. If we spray water into the battery pack and we cut a hole in it, we might start new thermal runaways, like the last red cell you saw there. But since we are at the same time getting water into the battery pack, we are cooling the other cells. So it doesn't really matter that we get a new thermal runaway or several new thermal runaways, because the water will do what it's designed for. After our test, we have seen tests in Netherlands last year that was successful. The NIPV did some testing there, burned 2 EVs, and in both cases as a success. And in France in June, we saw SDIS 91 do their testing, also successful testing. So we're starting to get the evidence that this works, and it will also keep the batteries most of the time extinguished. We don't have immediate reignitions. There are certain times in the process where it's more likely, but overall it's been working very well. In Sweden, we have some real-world operations. Here we had a vehicle with a thermal runaway in the battery pack, and it was extinguished with a fog nail. I'm gonna get back to that. The second one was a vehicle put out with a cutting extinguisher, and then we had an electric bus that was also put out with a fog nail. And the fog nail, when talking from the MSB perspective, the Swedish Civil Contingencies Agency, the fog nail is not a recommended tool. So this was something that was made not following the recommendations. But what we saw was that we got water inside the battery pack and it worked. Then I'm going to talk a little bit about explosions. Because I think that's the largest hazard we have to navigate through or around. And we have all seen those pictures. This was an explosion in a vehicle where we had the garage roof was blown away, the walls were blown away. And then we have different levels of this. This is also something you all have seen, the Jeep on the fire station that blew the roof up in the air due to a good explosion. This one, a compartment explosion, a very heavy explosion. And then we have this one here from one of the operations in Sweden. When they ventilate the window, we can see that we get an ignition right about now. There, but it wasn't a very heavy one. So it was an ignition of the gases, but not a solid explosion. And then we have this one from the US with 4 windows down. We have the vent gases in the compartment and it ignites. And what this gives us is that we have to navigate all those different events. It's not always super dangerous, and we can have a fire in a battery pack where we have the white gases, the smoke as I call it, but we might be able to do something about it. And our thoughts here is to handle it like a gas leak. If you have a flaming thermal runaway, then it's much better from an explosion perspective than if you have a smoking thermal runaway. And the firefighters have a lot of tools already in the toolbox if we think of it as a gas leak of a combustible gas. For example, this approaching a vehicle, we know that it's most likely that the pressure from the explosion will go to the sides. So if we approach the vehicle from 45 degrees, in this case, then we can get closer to the vehicle. If what we want to do is to ventilate it, this is a very good example from the Netherlands again, where they use a cutting extinguisher with abrasive to break one of the windows from the distance. And in that way, they get the vehicle ventilated. The other example is this one that I just showed you from Sweden, where they used a tool to break the window, wait for a while, because that seems to be like with a regular backdraft, that it takes a while for the oxygen to get into the compartment, and then we have the ignition. And if we now want to get water into the backpack, when can we expect a result? Because that will also vary. And it will vary because the tilt angle of the vehicle, if we are in the correct compartment, because we can have vehicles with several compartments, and there the rescue sheets are very valuable. And if we, for example, have large holes in the bottom of the battery pack, like Tesla, for example, have that their battery pack bottoms can burn away. And if we have that kind of construction, then this method will not work. So we need to be aware that it's not a single solution for everything. And also that cell and module size matters. And this is what I'm talking about here. We have 3 different sizes. The smallest size, they have a thermal runaway for 5 seconds. So if I get water inside the battery pack, it will be very fast for the cooling to work. The upper left, we have a 0.45 kilowatt hour battery cell. And that thermal runaway will go for 20 seconds. And in the bottom, we have a Volkswagen battery module with pouch cells, which will go through the module for 7 minutes. And since we are talking about cooling the adjacent cells, we can't expect a result from the cooling until we have the original thermal runaway burned through. And what that gives us is a timeline how we must flow water. So we must flow water enough long enough to as the thermal runaway. We need an additional cooling time and some extra time. And this, I think, can be frustrating for the firefighters, because we can stand spraying waters for like 7, 8, 9 minutes, and we don't see any results because the thermal runaway is still going on in the original cell. But then we need to be patient with it. And finally, I would like to show this video here. If this is what we have when the caller calls to the dispatch center, they say we have lots of flames, we have a lot of smoke. Battery packs are today very good designed. They are designed not to burn and to have a slow fire spread. This means that this, what we're looking at now, could be what the fire service sees when they arrive. That is nothing. So we need to be aware of that and use that time wisely to prepare for what could happen when we start to get this fire again. And also talking about good design, they are designed to be able to handle a single thermal runaway. And sometimes that works. And if that is the case, then we should not do any holes in the battery pack, because then we have a self-contained battery pack fire. And with that, I would like to go to my last picture. I'm just going to see if I can do that here. Here we go. So that was what I was going to talk about today. I sent the operational guidance in English to Olivier, and I think he will share it after this session here. And also I have a YouTube channel where when I do videos for the Swedish fire brigades, I used to do them in English as well to share them with the international firefighting community. So please go ahead and look at the English channel. Thank you very much.
Thank you very much, Paola. It was very informative, a lot of example, and we see that the size matter, and this is important to get prepared as much as we can. There are some questions already in the chat for you that we will take after all presentations. I would like that Amandine, you take over the control and you continue with your presentation.
Yes.
Perfect.
Okay. So thank you, Olivier, for inviting me to present some research insights about lithium battery fires. So I will explain you a little bit what is a lithium battery, some aspects of thermal runaway, and some tests we performed at INERIS. So here is a brief overview of what a lithium-ion battery is. So a battery pack is made of several modules, each of which is made of several cells. So the cell is a basic unit of the battery. Inside the cell, there are four main components. That is a cathode, which determines the lithium-ion battery chemistry, because in lithium-ion batteries, there are several chemistry. So the main common chemistry are LFP, lithium-ion phosphate, that is widely used in battery energy system storage, for example. And the other one that is widely used is NMC, nickel, manganese, cobalt, for example, in automotive application. The second component is anode, and the anode and the cathode are separated by a separator. And the whole system is worked in electrolyte, composed of a salt and solvent. So on the right, you can see a pie chart with a typical proportion of the chemical elements that we can be found in battery pack in a battery module of an electric vehicle. As you know, the lithium-ion battery are prone to thermal runaway phenomena. So this thermal runaway can occur when the battery is subjected to external aggressions, such as mechanical aggression, electrical, dysfunctional, or thermal aggression. Or a thermal runaway can also occur due to internal factors, such as manufacturing or design defects. It is the thermal runaway of one cell can propagate to adjacent cells, to the complete module or complete pack or rack, or even to the complete vehicle or complete system. Different effects can occur during thermal runaway. It can lead to gas and particle release, fire, explosion, as it was showed by Perola. Also projections of incandescent materials or small cells. So here is a summary of these different effects. So during thermal runaway of lithium-ion batteries, heat is generated, so that produce thermal effects, and also fumes. And these fumes are composed of flammable gases, toxic gases, and also particles. So we'll go deeper we'll go in more detail in the following slides about this composition of fumes. In some specific cases, projections can also occur. That is also called the missiles effect. These projections are mainly seen during fires in storage or recycling plants, or also in some specific cases of violent crash of electric vehicles. It's mainly due to the small cells that are in this type of pack on different type of vehicles or in bulk storage, for example. So lithium-ion batteries are involved in many accidents and in many applications. For example, from smallest as smartphone or scooter, through medium as cars, and also to the largest as battery electric system storage, BESS, also recycling facilities. You have here some examples and pictures of accidents that occur for these many applications. Here is an example of an accident that occurred on a BESS in the south of France in 2020. So it was a mixed electrochemistry of lithium iron phosphate and supercapacitor. It was a new container that is being put into service. So a fire occurred in a BSS container that contained batteries. And the difficulty in this case, it was that these BSS containing battery were stacked. There is a stacking of this container above another one. So it poses difficulty of access for firefighting services. And also in this site, there is a lack of nearby water points. So it was difficult to extinguish the fire. And also this container was equipped with an extinguishing agent based on phosphate salts, but it was inefficient to tackle the fire. So at Ineris, we have different safety platform to characterize the lithium-ion batteries runaway. So here is the first platform we have that is called the STIF platform. In this platform, we are able to perform different type of tests: mechanical abuse test, electrical abuse test, thermal stability test on batteries, to characterize the effects and also to analyze the gases emitted during the abuse test and also the particles analysis. The second platform is the fire platform that is used also to perform some fire tests, but also mechanical, electrical tests on larger batteries, since the test chamber higher size. For example, we have a very large fire safety chamber of 1,000 cube meter that is used to perform a test at pack level or also at electric vehicle level and also system level. And in this platform, gas analysis and particle analysis are also analyzed. So we have different type of measurements, such as physical measurements, in-generation characterization, and online gas composition measurements, including smoke and particles. And also we perform water sampling and composition analysis. So I will show you some example of results we have. So here is the gas composition of 2 cases. So on the right, it's the typical composition of battery fire when we have little fumes generation, so it's mainly fire. So in this case, the main gas produced is CO2 at more than 90%. And on the left, it's a case where we have only fumes. And you can see that the composition is completely different, with a lower amount of CO2 and a higher amount of flammable gases. So it was here represented in this graph. In the case of fumes, we have highly flammable gases such as hydrogen, methane, ethylene. Also, both toxic and flammable gases such as carbon monoxide and also carbonates that are the solvents used in the battery. And also highly toxic gases such as formaldehyde and HF, and in some cases POF3 that is also toxic. In this table, it's just the report of the explosivity limit of the flammable gases and the toxicity threshold of toxic gases we can find in the fumes during thermal runaway of a battery, a lithium-ion battery. The gas composition can vary also with the chemistry. So in this table, you have an example of a gas composition of the two main chemistry we found in lithium-ion batteries, so lithium iron phosphate, LFP, and NMC. So the combustion is higher with NMC chemistry, so we have a higher amount of CO2 and CO. Whereas with LFP, it's mainly vaporization of the solvent that is in the battery, so a higher amount of solvent, named carbonate, are found in the fumes. So there are less combustion, and also fluorinated spaces are quantified in a higher amount for LFP because in LFP, generally, there are more quantity of electrolytes, so more salts that decomposed into HF. The state of charge also impacts the reactivity and the gas composition. In this graph, you can see a short circuit test performed on a different state of charge of the battery. So more the state higher state of charge leads to higher combustion process, higher risk of combustion, so with flames. And the decrease of the state of charge leads to more fumes. So higher state of charge means higher thermal effects, whereas lower state of charge means lower thermal effects, but higher amount of gas produced, and so higher risk of explosion risk. So here it's for talking about risk explosion. So under certain conditions, for example, underground car parks or garage, accumulation of gases emitted by the thermal runaway of the battery can generate an explosive atmosphere that can lead to an explosion. So here it's a short video. So it's a short video that shown that an explosion can occur in a garage. So it was an hybrid Jeep vehicle, and it can be violent in some cases. This explosion can also occur with a small number of lithium-ion cells in thermal runaway condition, and of course it depends on the environment and so on. So you have here another example. One in the center of the picture is BSS, an explosion that occurred in a BSS, and on the left it's a Tesla, so it just shows fumes that rapidly ignite and go after to fire. So the risk of explosion can need to be into account during extinguishing process. So it's the Jeep video that already be shown by Perola. So it's just to show you that water-based agents may extinguish the flames, so it reduces the thermal effects, but extinguishing the flames does not mean that the thermal runaway reaction has stopped. Thermal runaway reaction continues, and flammable gases can be produced, as I've shown you just before. So the risk of an explosion is present and need to be taken into account. So the risk is shift from thermal to explosion. So regarding particles emitted in the fumes, so the particles is also variable and the nature depends on battery chemistry. So the particles can be found in the smoke, but also near the scene of the incident, around the vehicles or inside the container for BSS application. And the particulate emissions significantly differ from combustion engine vehicles. So on the pie chart here, you can see an example of a composition of particles that was measured during a NMC battery pack fire. So you can see in this case a high amount of fluoride in the particles and heavy metal that are found in the battery. So manganese, nickel, cobalt, and lithium. These metals, cobalt, nickel, manganese, lithium, and fluoride, are found in a very higher amount in battery electric vehicle fire compared to combustion engine vehicles fire. So it is shown by this EMPA study during comparison of the fire of electric vehicle and internal combustion vehicle. Here is some samples that were taken from firefighters' clothing before and after an extinguishing test performed at Ineris on an EV battery pack. So the lighter bars on the histogram correspond to samples taken before the test, and the darker bars to samples taken after the test. So red colors correspond to sampling on the jacket, and the blue one on trousers. So it can be seen that contamination of firefighters' clothing is observed with metals. So the same as we found in particles, lithium, aluminum, manganese, cobalt, nickel, and also copper in this case. And also fluoride compounds are detected on the firefighters' clothing. And in a higher quantity on the upper part of the clothing, so on the jacket, compared to the trousers. So it means that the decontamination of the clothing need to be to account and is recommended after responding to lithium-ion battery fires. Regarding water runoff contamination, so there are different strategies to tackle a fire. So the first one is external cooling and smoke abatement of the fumes. So in this case, the water runoff have shown some contamination with cobalt, manganese, nickel, and lithium also. That was shown in the water runoff composition after intervention. The other possibility is battery immersion or electric vehicle immersion. In this case, the same components are found in the water. And the last one we studied is the direct contact of water. So the water is directly applied to the battery fire. And here you have the results of some analysis we performed recently on this water after test. So different type of tests were done. A sprinkler test, so we put a fire on a lithium-ion battery pack, and we trigger sprinkler system on it. We performed also medium density form. So it was a picture just 2 slides before with the firefighting intervention. And the last one in green, is a high density form test. And then we analyze this water, and you can see that this water is contaminated with metals, the same nickel, manganese, cobalt, lithium, aluminum, also presence of fluoride. And for foam test, we observed the presence of sodium and sulfur at a higher quantity for one of them that is coming from emulsifiers used for this test. So it's necessary to take into account the potential risk to the environment of the water runoff lithium-ion battery fires. And in some cases, we can also quantify some organic carbonates in the water. It was not the case in this last test, but we observed this on a previous test. So here is just another cases. Here, before I talked about lithium-ion batteries, but it exists another type of battery that contain lithium metal. So it's not lithium-ion batteries, but it's lithium metal polymer batteries or battery containing lithium metal. So it's different technology. And in this case, the reaction is a little bit different with more temperature reached, superior to 1600 degrees C. And we'll see on this video the projection of molten metal, a fast propagation to the whole system. So it was a bus, electric bus in Paris. And here it's lithium metal polymer battery. And you can see the projection of lithium metal at several meters from the bus, and a very high and hot flames. So it's okay, and here it's a complete fire of the bus. Sorry. So in this case, it's a really fast combustion, and it can pose some difficulties to extinguish. So, however, we performed some tests at INERIS on this technology. So these tests have shown that water may be used for this type of fire, but it didn't extinguish the module that here under thermal runaway. It can just limit the spread of the fire, but it produced toxic and flammable gases. And here in this case, we observed a phosphine emission during the extinguishing fire that is highly toxic. So in this case, it's important to limit the use of water on this type of technology. So to conclude, donc regarding lithium-ion batteries, thermal runaway of lithium-ion batteries, fumes contain both toxic gas and particles. So fumes might be flammable and also contain HF. During extinguishing process, be careful to the shift from thermal to explosion risk. The clothing of firefighters can be contaminated by chemical elements specific to batteries, such as heavy metals and fluoride. And runoff water can be contaminated with metals and electrolyte solvents. So retention is recommended. So here is just an overview of ongoing research on this topic. So we continue at INERIS to perform some extinguishing tests with other fire suppression methods, and to go deeper to the toxicity assessment of lithium-ion fumes, particles, and ecotoxicity assessment of firefighting effluents. So here just some report that can be useful to read. Thank you for your attention.
Thank you very much, Amandine. So it has been also, again, very informative, and we better understand that the chemistry of the battery is very important. And depending the type of battery, there are different type of gas that could be emitted and different kind of particles. And also an important aspect is the quantification of the contamination on the garments, on the equipment of the firefighters. I think this is a topic that required a lot of attention in the future. The cleaning is always a challenge, but it's really important in that case to pay even more attention because of the contamination with heavy metals. So thank you very much. There are many questions for you in the chat, so in the Q&A part. So look at it and get prepared for the last part of the webinar to answer the question from the different participants. Please, Lena, please take over the control and present us the technologies that your company has developed.
Thank you, Olivier and Amandine. So my name is Lena Ulveman. I'm head of our training and method development team at Colcat Systems, based in Sweden. And I'm a fire engineer, and my job is all about helping fire and rescue services to use our technology and our methods and techniques in a smart and safe way. So I get to work closely with firefighters and organizations all over the world, learning from real incidents and testing new ideas, making sure that what we do actually works in practice. And that really ties into our bigger purpose as a company, what drives us and what shapes how we develop our products and our trainings. So our vision is simple. It's safer, cleaner, and more efficient. Safer for the firefighter, cleaner for both firefighter and the environment, and efficient in terms of water use and time and resources. So I'm going to give you a brief background of who we are and what we do, and then I'll move on to the specific EV method that is on focus for today. So Colcat Systems, we manufacture and sell an ultra-high pressure lance known as Cobra. It's used by fire and rescue services all over the world. We've been doing this since 1997, so we have more than 25 years of experience. Our main customers or users are within the fire and rescue service, but the system is also used in other sectors such as airports, maritime environments, power plants, coal mines, refineries, and even within car production. So the coal cutting technique actually has its roots in cutting work within explosive and combustible environments. It was first used with cutting refractors, cisterns, and pipelines at refineries. But in the mid-90s, the Swedish fire services tested it as a way to make ventilation openings. And when testing, it was quickly realized that this method also, when the water jet broke through, and the temperature inside the compartment dropped drastically. And that discovery became the sort of foundation of what we now know as Cobra. So Cobra lets firefighters cool the hot fire gases from a safer position outside the fire compartment. And it does so by using an ultra-high pressure water jet, which is mixed with sort of a cutting media called abrasive, and it can cut through any building material in just a few seconds. And once the jet breaks through, it makes only a small hole which won't let any extra air in, and the fine water mist that follows creates a huge cooling surface area, which makes gas cooling both fast and very efficient. All this is done using only 60 or 30 liters per minute of water, depending on what system you have. So Cobra is not for just one type of fire, and over the years, the system has been adapted for many different kinds of incidents, and we always develop the methods together with fire and rescue services. Examples of use are well, yeah, hidden fires, attic fires, industrial fires, and yeah, more recently, EV battery fires. And because Cobra is used in so many different types of fires, it's not just about having the right tool, it's about knowing how to use it efficiently in each situation. And that's where Kolkat Academy comes in, where we develop the methods, tactics, and conduct training for using Cobra. And we provide courses ranging from basic operator courses to instructor courses, refresher, and more targeted courses as incident commander course, and of course, the new Cobra and EV battery fire course, which focuses on one of the most complex challenges firefighters face today. So with that said, let's look at the development of this method of handling the propagation in EV fires. So we had quite a journey to develop this method, which would not be possible without help and from experts in the field, fire and rescue services, car manufacturers, and national contingencies agencies. And in 2008, Kolkat Systems, we were contacted by the car manufacturer in Czech Republic, Skoda Auto, and they told us that they were using Cobra to stop propagation when having an event in their factory. And this had they been doing successfully in over 20 traction batteries. So during 2021, we were carrying out tests on extinguishing battery packs with Cobra, and we had very positive results. And overall, the project showed that it is possible to stop propagation in a battery pack by using internal cooling with water. Though we had not figured out a method quite yet, so more tests had to be done to develop a feasible method that could be recommended as a, so to say, a generic method for fire and rescue services to access and extinguish a propagating or stop a propagating lithium-ion battery in a vehicle. So a little bit of repetition from what Per-Ola said. So the Swedish Civil Contingencies Agency initiated a project to create a method for handling propagating batteries, and also to answer a lot of questions about risks and working environment for firefighters. So we had the facts. Scientific studies confirmed that the only way to stop a propagating lithium-ion battery was to get water inside, or any available cooling media inside the battery pack, and cool the modules. But question remained on how do you get inside the battery pack? And for this, all the FRS needs a proven, repeatable method and a tool that could do the job. So that project was joint effort. It was battery experts, car manufacturers, and tool developers, including us, Kolkat Systems, with the main focus to find a working method on how to cool the batteries with fresh water only, since that had already been confirmed in earlier studies that that was the key on stopping the propagation. So with the goal of actually define a method on that could actually be used by firefighters based on tools that was already accessible for the fire and rescue services. This result, as Per-Ola said, was demonstrated in a demonstration report and one guidance document on how to handle thermal events. And these results were then shared with Skoda Auto, and they carried out more tests on their own, battery pack level and full-scale tests, and in all scenarios, the fire propagation was stopped. And the phase after that was in the Netherlands, where the Dutch Institute and IPV carried out similar tests and trials together with Stellantis, where we contributed by sharing experiences and observations and training the crews on the method. This also resulted in a method and a guidance. And ever since, we know of several tests done by other organizations, and most recently, as Per-Ola mentioned as well, the SIS in France. We're waiting for their report coming shortly, and also the NFPA in the United States. We're waiting for a final report to be released in December, as I know it. So what is the method then? So the method I'm about to present is based on the guidance published by the Swedish Contingency Agency, known as MSP in Sweden. So what we're going to do first is to actually start the operation by extinguish it as a normal car fire in line with the standard operating procedures. And by then we can confirm if it's an EV fire or if it's not. If it's an EV fire where the traction battery is not involved, then we can continue extinguish it as a normal car fire, because the traction battery will get involved eventually. If the traction battery is involved, we consider doing a intervention or not, depending on the situation, the scenario. Where is the car placed? Is it in an underground garage or an open parking lot? If we decide on continuing or doing the intervention, we are going to start by we're going to extinguish the flames. We're going to look for hotspots with our thermal imaging camera. We'll deploy Cobra to close to the hotspot, not necessarily at the hotspot, but we want to establish an internal flow of water to cool the battery cells. And we'll continue monitor this with the thermal imaging camera. We might have to redeploy Cobra if nothing happens. As Per-Ola also said earlier, that the modules burn differently long, so patience is key to success here. Our target is to get below 50 degrees Celsius over time so that it's stabilized, and we'll monitor the temperature for a minimum 15 minutes or however long we need. If the temperature rises, we redeploy Cobra and we do it all over again. We're gonna extinguish any remaining fires as well in the vehicle's interior and exterior with a regular firefighting branch. So this full method is not from 1 to 7. It's a dynamic deployment of Cobra and searching for hot temperatures, and you have to stand back, evaluate, redeploy if the situation demands. I'm going to show a short video of this, and afterwards I'll quickly share some case studies on real interventions. All right, so a quick walk through some real incidents that has happened with where Cobra was deployed. Norway, a vehicle pulled over, had hit debris on the road, and the driver pulled over as soon as he saw smoke and flames coming up from underneath the car. The crews first used conventional firefighting to get rid of the flames, and then was Cobra deployed for 3 times for 5-6 minutes each to cool the battery until the propagation had stopped. And in the Netherlands, there was a car charging at the time, and the crews could see white smoke coming from the car. It was a hybrid car, and they quickly realized that this was the battery that was in off-gassing mode, so to say. And they called for Cobra, and after 20 minutes of intervention, the propagation could be deemed stopped. So fast forwarding here. This was a Volvo XC40, also a hybrid, where the fire service in France, they have reported several successful EV interventions, and this was also on a charging hybrid car, where they started by extinguish the flames, but the smoke continued to coming from the battery pack, and that's when they realized that we need to get inside the battery. And so Cobra was deployed, 2 deployments of 10 minutes each. The temperatures dropped and the smoke dissipated, and the vehicle was then towed away without any reignition reported. So 300 liters of water used in that one. In Tempe, they got called to a Tesla fire burning. You can see the flames coming out from underneath. They deployed Cobra for approximately 10 minutes, also 300 liters of water to stop the propagation. And one more from the Netherlands, my last one. This is the department in Rotterdam, who answered to a call on a EV fire that's also had hit some kind of debris from the road, putting the batteries in thermal runaway. Again, the driver pulled over, and when the crews came, they used these Dutch agreed procedures on how to handle a propagation in the battery. They deployed Cobra for 4 times, 4 minutes each, to flood and to cool the battery, and the successful stop of the propagation. That's me. Thank you.
Thank you so much, Lena, for the introduction of your system developed by Colcut. Very interesting. Also the history of the development of the technology I found very interesting, because it's exactly what we would like to do to support in the Direction project, this co-creation. So you started in 2018 with Skoda, had some different tests with other companies, so Stellantis. So, and working together, you develop a solution that fits the needs, and with the fire brigade also help to minimize the amount of water which is used, and avoid that we have propagation, especially between different vehicles, if we are in a place where we have many vehicles stored together. So very much thank you. And now I think you can also look at the chat or look at the Q&A part of the webinar. There are many questions to you, and a colleague from the Netherlands also who was involved probably in the NIPV test offered to contact him, Theon Sepayens, probably a person who is familiar to you. So let's go to the next step, which is the panel discussion and question and answers. Perola, I will take the question in the order of the presentation. Per-Ola, did you check the question which were addressed to you by different participants? Can you take them?
Yeah, I will be happy to do that. I mistakenly went to the chat and didn't see any questions. So now I realize there is a question and answer part. Yeah, the Q&A as well.
So there is a first question which is about, with some battery packs, the modules are in some sort of casing. Would you consider it an option to use a fork nail when you put in the casing, but are sure that you are not going into the battery module? So there is this question about using in some time fork nail or a system which are more like a Cobra or other system.
Yeah, I would say what we finished in the MSP project, in the Swedish Civil Contingencies Agency project, was that only use approved tools when you go into the battery pack. If you're spraying from outside the battery pack and you have a hole that you can like see and get water into, that's fine. But as soon as you enter the battery pack with something, you should have an approved tool. And the fog nail is an interesting example because we have had those incidents in Sweden where they used a fog nail and they said, well, we only use the holes in the battery pack that are there already, and they entered the fog nail into that. And that is one of the risky things as we see it, because if you use an existing hole, then you don't ground the tool to the cover of the battery pack. Which if you hit a bus bar in the battery pack, that could be dangerous for the firefighter.
Okay.
So, and I'm sure there will be more knowledge like in the coming years about electrical safety and the risk analysis. But for now, we say just use approved tools.
Okay, there is another question which is about how do you determine as a firefighter that propagation has not occurred to other cells due to the good design or not so good design? So
yeah,
how do we handle
that is a very good question that we still doesn't have a good answer, and this is where we think it is a kind of a waiting game. When you have had one thermal runaway in one cell and you get there and nothing is showing, then in our guidance we say prepare as you would if there is a fire in the battery pack. So do everything in preparation, and then you start using the thermal imager, and you make like every 5 minutes or every 10 minutes with some kind of interval, you look at the same spots over and over again, and you see if you have a rising temperature, if you have a lowering temperature, and that will give you a hint on what direction you're going.
So with a thermal camera, like a thermal camera.
Thermal camera, yeah, and be aware that this will be an operation that can take some time. So don't expect to leave there in an hour or so, but stay there until you know that it's a safe situation.
Yeah, Lennart said that the patience can be a very important aspect during fighting this kind of fire, especially if you have a large pack. And you demonstrate that well, this as well, Per-Ola, with your video showing that you have, depending the size of the battery, you have to expect a longer impact. There is another question which is about, is there a difference in fire reaction when you use a cold cut system or on a pouch or on a cylindrical prismatic battery pack?
Is that for me or for Lena? Lena, you'll take that one?
Each of you, any of you, I think.
From experience, there is a different kind of reaction. I don't think it's because of the cold cutting, the ultra high pressure. It's because of the different types of cells and how they react in thermal runaway. So our experience is based on how easy it is to cool the cells or the modules more correctly, depending on what configuration it is. And cylindrical cells are often placed with insulation foam, so making it harder to get this cooling flow of cooling water, and so that demands a different tactic. But yeah, we managed all types of the most used battery cells. We managed to stop the propagation with.
Yeah, thank you.
Yeah. And I could add to that a question that is often asked, if because of this insulation that they have in the cylindrical cell packs, they say that it's impossible to get water there. But what you have to consider is that there has been a thermal runaway with a lot of gases pushing out from the battery cell. So that will create an opening where the water can flow. So it can work even in the cases with good insulation.
Yeah. So there is another question from Yonio, KGPSP. So he's explaining that, or he's asking, there is a recommendation from the manufacturer to avoid damage on the casing. So how do, what is your position regarding this? If we need to cool down, we need to open it somehow, right?
Yeah. I can take that one, because that's a question we have been wrestling with in when doing the Swedish guidance. Because if you would consider this a building instead, and we went with a fire engine to the building, and then we had a fire inside the building, we wouldn't ask the builder, is it okay for us to enter the building?
Yes.
We would use the knowledge we have and the tools we have and make risk assessments. And it would be so helpful if the builder told us all the hazards there was in the building, so we could do safe operations. And in this case, the car manufacturers are making instructions for the fire services that are very general. They say you should never do this and you should always do this. But what we have in reality is we have so many different situations that depends on where the vehicle is located, how much it's burning. Not all cars are burning like we see on the YouTube videos. We can have those small, slow cooking fires that can take hours, and we need to address them. So it would be more helpful if the car manufacturers started to inform us about the risks, show the videos they have and show the tests they have done so we can learn from it, but not give this kind of detailed instructions about do's and don't.
Yeah, so it's more rather the experience of the firefighter, which is important, and also understanding the situation. As you said, you do your own risk assessment of the situation, how the fire might develop, and so on. Now I have a question to Amandine, and this is about how do you compare the risk of LFP and NMC type of battery when looking at the difference in gas composition? So is there a strong difference in the gas composition for these different type of batteries?
Yes. As we have shown in some example, on LFP, there are more flammable gases in generally, compared to NMC, where a fire is more observed, so with more flames and more thermal effects, compared to LFP, where it's more venting and gas emission fumes. So we can say that LFP is maybe more subjected to explosion risk compared to NMC that is more that are more thermal effects of fire probability compared to LFP.
Thank you. I think this brings clarity. The next question is about, can you make an indication of what battery size can result in an explosive atmosphere of a certain volume? Can an electric bike battery create an explosive atmosphere in a shed, in a living room, in a warehouse? In other words, how does the kilowatt hour compare to the volume?
It's a really good question. We can estimate that lithium-ion batteries can release between 0.5 to 2 square meter of gases per kilowatt hour. So if we consider that the explosivity limit is around 7%, we can say that an EV bike battery, lithium-ion battery for a bike can cause an explosive atmosphere in a 20 square meter room, for example. So it's a really fast calculation. It depends of many parameters, the state of charge of the battery and so on, and the chemistry that emits more or less gases. But we can estimate that lithium-ion battery of a bike can create an explosive atmosphere in this range of size of room.
Okay.
As you can see in the garage in the video, it was a Jeep electric. It was an hybrid vehicle. So it's not a really high density battery, maybe several kilowatt hour, and it creates an explosive atmosphere in a garage.
Yeah. Thank you. I think it brings some order of magnitude, some understanding, and of course, if you have a big room, so you have more chance to dilute the flammable gas and to be below the flammable limit. So the lower flammable limit, which is safer, but in a more confined space, like in a container, like the BESS accident you mentioned during your presentation, we have more chance to have explosion and so on.
Yeah. And
So
in this configuration, there are not a lot of free spaces. It's it's a lot of
more hazards.
majors. Yeah.
There is a question regarding the garment, so the clothes that have been used for the test at Ineris, where you have measured the contamination on the equipment. Did Ineris provide the equipment, or it was the equipment from the firefighters that they brought themselves?
Yeah, it was the equipment of firefighters. So there are some contamination before. It's true. So it's come from intervention from their part. Yeah.
Yeah, the cleaning I was discussing with Milan Dubravac from CTIF, the president of CTIF, and he said that the decontamination of the garments of the clothes is really a big issue. Yeah. From Professor Jose Lopez, different experts have already said that the use of water in firefighting can seriously increase the release of explosive and highly toxic gas, raising the risk for firefighter. How can one analyze the risk benefits of using water in firefighting, with particular concern for fire in underground parking lot? So I'm not sure with the first sentence.
I feel for that question because that's also something we have been working on a lot. And we must differentiate between the pollution of the environment and the explosion hazard. And about the pollution of the environment, I think if we get water into the battery pack, we have seen that we can have very many cells and modules don't burn. So in that way, okay, we get a polluted water, but we will have so much less pollution overall. And since we many times can do it with a limited amount of water, if we want to, it would be possible to collect the water or a lot of the water anyway, and get that to the recycling or whatever you do with the water. But the explosion hazard, I'm not sure if I agree that we get an increased explosion hazard, because that would be if we get it on lithium metal cells. As far as I know, since we are cooling the cells and we are getting water into the battery pack, I haven't seen that we are getting any more flammable gases or explosive gases due to using water.
Yeah. So I think we need to better analyze the situation case by case, as you said, to really conclude this kind of trend. There is also a question: how can we know that putting water inside the battery with Cobra method will not have electric danger for the user? For the users, it's a question for Lena, I think.
Yeah. How can you know? It's I wouldn't say it's a yes or a no. It's risk assessments depending on the state of the battery. Is the car charging? Is it in a crash? Do you have is there a risk of closing the circuit with Cobra? The likelihood of that happening is kind of small, I would say. You need to close the circuit with Cobra, and electricity takes the way of least resistance. So the likelihood of getting electrocuted by using Cobra on a traction battery is really small. That would be my answer. We do have a risk assessment along this, and I'm happy to answer that in a longer way.
Thank you. Thank you. There is another question regarding the use of robots, so combination of robot with Cobra system to have the user, the firefighter, at a certain distance from the operation. Are there any development on this type of new technologies?
Yeah, I think that's an amazing idea, especially if we're talking about energy storage systems. We are not in any projects with that as of now, but I do know that there are fire and rescue services looking into it. But I'm keen on knowing what the results are, and we are happy to help with that.
Okay, so I think we have addressed more or less all questions, because the last question is also about the risk of having, is there a danger of electrical shock when extinguishing a battery fire with cold cut Cobra? I think we have addressed this question, and we are running a little bit over the time. So I think it's, for me, the time to conclude this presentation, and to really thank you all, Lena, Amandine, Perola. I really want to thank you for bringing so much knowledge in a few slides and in 1 hour. I think it will be very helpful for all firefighter, emergency responders who want to know more about how to address a fire with batteries, lithium-ion batteries, electric vehicles. So thank you very much for your contribution. And I would like also to thank all the attendees who stay with us for more than 1 hour. We are up to 100 participants today, so it's very nice. And please, if you want to see more webinars, stay tuned with the QR codes that you see on the screen. Our next webinar will be on the 28th of November, and it will be about the use of drones, the use of this kind of technology for difficult operations. And we will have, as for today, the firefighter emergency responder point of view, the vision from the research, and a company presenting their technology, or even 2 companies will be presenting. So thank you all, and see you next time. Bye-bye.
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 Bye. Thank you.